开始上课。好，那就再讲一下接下来这几周啊。今天我再上的是 lecture，主要的课程内容应该今天就会结束了。OK， 那我们 deep learning 这一段其实教的蛮快了。那我觉得如果是大家是在烦恼从考试这些角度去想的话，其实
All right, so today I will first discuss two examples of second order circuits because on Wednesday we will have our last quiz. Okay, so in the Wednesday's quiz that will basically cover the contents related to second order circuit, RLC circuit. 好，星期三我们小考最后一次，那最后一次小考的范围就是二阶电路，RLC 的电路这样子。好，所以今天我会先讲2个二阶电路的例题，然后我们会继续上11章。Okay. Do you have any questions before we start it? All right, so I'm going to write 2 examples. Okay, there are different ways you can solve the second order circuits. And then during the calculation, for example, if you remember how to derive alpha and omega 0, that help you determine if the case is underdamped, overdamped, or critically damped. And then from that, you may have different equations to describe underdamped cases or overdamped cases or critically damped cases, then you can start from that. If you don't remember, you can start from writing KCL and KVL equations, and then that will lead to a second order differential equation that describes this circuit, and then from that you solve for the roots, 2 roots of this the second order differential equation, and then go from that. 好，所以你有一些不同的方式，如果你做得很熟悉，那你记得 alpha 跟 omega 0怎么计算，然后你记得 characteristic equation 是怎么写出来之后，你知道它是 underdamped 还是 overdamped 还是 critically damped， 那你记得它的式子的话，你也可以直接写。那但是如果不记得的话，像我们就直接从头开始写，最主要就是从 KCL、KVL 或者是 node analysis 写出描述这个电路的2阶微分方程式，写出来之后解这个 S 会有2个解，那你看 S 是实数还是负数，还是相同的值，可以判断它是哪一种 case， 然后再带进去算前面用我们的 initial condition 算前面的常数，这样子也可以。那 underdamped 的 case 比较复杂一点，所以不论是哪一种 case， 请你回家一定要练习计算一下，因为计算的过程本身是需要熟悉一下。你在考试，因为我们是有限的时间，所以计算的过程你一定要熟悉一下。好 ，OK， from this I'm going to write KCL. Okay, so at this node we have 3 current that will sum up to 0. Okay, so the current of an inductor, the current of a resistor, plus the current of a capacitor. would sum up to 0. And then we know that for the inductor, there is a relationship between its current and the voltage. Okay, so now we have two equations. We have two unknowns. One is the current of an inductor IL. One is the voltage of a capacitor V. Okay. Actually, let's start for IL, but you can, once you find IL, it's easy to find the voltage V, okay? So I'm going to use the second equation and put it into the first equation that would have IL. And then V is equal to 8 dIL dt divided by 20K. Okay, dV dt is now the derivative of this term. Okay, so 8 times dIL squared dt squared equal to 0. Okay, if you are going to look for V of t first, then it's easier to replace this IL with the second equation first, so that you have the second order differential equation in terms of V instead of I. 好，所以我把第二式 V 跟 I 的关系，把它带入第一式这个 V 的这个地方。好，所以得到下面这个式子。然后呢 ，we just rewrite this. Okay, so here we will lead to this second order differential equation in terms of IL. Okay, the constant term is equal to 0 because in this circuit we have non-zero initial condition, but we don't have external excitation. So we don't have a voltage source or a current source. So the constant term is equal to 0. Then we only need to look for homogeneous solution in this case. Okay, remember we need to assume that the homogeneous solution, which is also the total solution in this case, is in the form of A times exponential st, and then we put it back in this second order differential equation. 好，所以你假设这个，或者是你记得这个式子怎么写成它的 characteristic equation， 你可以直接写。好 ，A exponential st 把它带进去。所以第一项 the first term is the derivative of IL squared divided by t squared. So that we will have s squared times a exponential st. The second term is equal to 400 times dIL dt. Okay, so 400 times dIL dt. And then the last term is equal to 10 to the 6th times IL. Okay, so that we can rewrite this to get our characteristic equation. Okay, so this part is the characteristic equation that we will use this to solve for 2s. Okay, so ignore the trivial solution that this part is not equal to 0, so that s squared plus 400s plus 10 to the 6 is equal to 0. Okay, s equal to 2 minus 400 plus minus 400 squared minus 4 times 10 to the 6. Okay, so we have two complex roots.好，算出来之后是复数。好 ，so one root is equal to minus 200 plus j 980. The second root is equal to minus 200 minus j 980. Okay, so that we know this is the case of underdamp. « 好，那如果你记得的话，我们会把这个 characteristic equation 跟我们的这个标准式子比，你可以算出阿尔法跟这个 omega 0。好，那比较它们的大小，也可以知道我们是什么样的 case。好，然后呢，如果知道它是 underdamp， 我们也可以算 omega d 980。Okay, so to this point, we have two complex roots so that we know the current is equal to A1 times exponential minus 200 plus J 980 T plus A2. « 好，所以我们现在已知 IL 长的是这样子。那最后呢 ，finally we need to look for A1 and A2 by using initial condition given in the question. Okay, V is equal to 0 when T equal to 0. I is equal to minus 12.25 milliamp when T equal to 0. 好，所以我们把 initial condition 把它带进去。Here I'm going to rewrite this equation by having this term out of by breaking the exponential term into two terms. Okay, so I rewrite it in this form. You can also leave it as it is in the previous page. 好，你可以写成这个形式。好，那大家有没有印象？我们因为你把 exponential 负200t 可以提出来，后面这个 j 980t 跟负 j 980t 可以把它换成 sin 跟 cosine。好，那前面一样有一个系数。好，所以我把它换成这样子。 Okay, so IL when t equal to 0 is equal to K1, which is minus 12.25 milliamp. So we know that K1 equal to this value. And then from the second initial condition, we know that V is equal to L di dt. Okay, so di dt when t equal to 0 is equal to 0. Okay, I'm going to write it out, the differentiation of this part. 好，你不一定要抄，我只是因为有些同学他想要知道一下这个计算的过程。好，那 the most important point is that you need to write it out at least one times by yourself. di dt. Okay, so keep this part. Take the differentiation of these two terms in the in this braces. 好，负 exponential 负200t 不微分，后面微分。好 ，cosine 微分是负 sin。好，那其实这个因为负 sin t 等于0带进去是0，好，所以实际上你写的时候不会那么复杂。Okay, so all the sine terms are equal to 0. All the cosine terms are equal to 1, so that we have 980 K2 minus 200 K1 equal to 0. Okay, so from that we can calculate K2. Okay, so now we know K1 and K2 and put it in the homogeneous solution here so that we have the total solution equal to this amp. Now, if you are interested, you can practice how to write the voltage V is equal to 100 times exponential 200t times sine sine 980t volt. 好，你可以回家练习一下哈。这个是 V 的这个式子 ，when t is greater than 0. Okay, so again, the first step, important part, is to write the second order differential equation that describe the circuit, and then from that, we will need to look for n general particular solution and homogeneous solution. In this case, particular solution is equal to 0, so we only look for homogeneous solution. In other cases, depending on the format of this constant term or this term related to the independent sources in the circuit, you would need to assume the particular solution in the similar form as this term. Okay, so for that, you will need to calculate particular solution and then homogeneous solution, and then total solution is equal to the sum of these two solutions. For homogeneous solution, we set the constant term equal to 0, and then we calculate two roots. And then from that, we would be able to determine if it's under-damped or over-damped or critically damped. And then for different cases, they have different form of this response. Okay, so in this case, we have under-damped, so we assume that IL is equal to this equation. So we only have two remaining unknowns here, K1 and K2. So by using two initial conditions, we will be able to find K1 and K2, and then put it back in this equation. Then we have a final homogeneous solution, which is also the final total solution. Okay, and you can calculate V by replacing IL in terms of V in this equation. 好，所以如果你要直接算 V 的话，你把这个 IL 用这个 V 的式子把它带进去。那你把它带进去呢，会有个积分的符号，所以你需要每一项再微分一次，所以会得到用 V 来表示的这个二阶微分方程式。那你就一样的方法去解，所以可以解得出来。好，那we will have very similar questions of very similar questions in the quiz or final exams. Okay. The second example. Also last time we have one example that within the second order circuit we also have ideal operational amplifier, and then we also have very similar cases in the practice problems that you can take a look. 我们上次还有我们练习的作业里有这个二阶，就是电路里面是有电感、电容跟电阻，然后呢有这个理想的OP 放大器，好，所以请你回去也要复习一下。 Okay, in this case, find IL for t greater than 0. There's no initial condition given, but we can calculate that. Before t equal to 0, this is equal to 0. Remember, u of t is a unit step function, which is equal to 1 after t equal to 0. Okay, so it's equal to 0 when t is smaller than 0. Okay, so when t is smaller than 0, this current is equal to 0. So there's no current in this path. And then we have a capacitor, inductor, and then resistor that are connected to a 10-volt source for a long time. Okay, so if the circuit holds on this state for a long time, an inductor look like a short circuit while a capacitor look like an open circuit here. So there's no current going through this path. There's only current in the 3 ohm resistor. Okay, so we know that the initial condition we have IL. There's no current here, okay, because it's an open circuit. So 0 amp. And then the voltage across a capacitor is equal to 10 volt. Okay, so we have these two initial conditions to start with. And then we start to draw the circuit for t greater than 0. So now we have a current source equal to 2 times exponential minus 3t. And now the 10-volt source is disconnected, okay? Alright, so right now we need to solve for the blue circuit for t greater than 0. I'm going to first write KCL that IS is equal to the current of the capacitor plus the current of IL. And then we can write KVL. VC is equal to the voltage of the inductor plus the voltage of the resistor. Okay, so we have two unknown, VC and IL, and then we have two equations here. Okay, so I'm going to use the second equation in the first equation to replace VC in the first equation. 好，因为我们要求 IL， 所以我把第二式这个 VC 的部分带进第一式，把这个 VC 的地方取代变成 IL。Okay, so we write this that IS equal to 1/2 times the VC dt, which is the differentiation of this part. So we have dIL dt square plus 3 dIL dt plus IL. Okay, so now it leads to this second order differential equation to be solved in terms of IL. 好，所以最后你一定会解到一个二阶微分方程式，只有一个未知数。好，然后我们就要解这个未知数。Now we have independent current source providing charges to the circuit, so we have a non-zero term here that we will need to look for a particular solution and homogeneous solution. Okay, for a particular solution, we assume it is in the same form as the current source. So assume it's B a constant times exponential minus 3t, and then we put it in the previous second order differential equation. 假设它是一样的形式 exponential 的形式，把它带入这个式子里面。好，第一项是1/2，然后 IL 微分2次，所以-3乘以-3。好 ，the second term 3 divided by 2 times the IL dt minus 3, and then IL. Okay, so that B equal to 2, we have particular solution equal to 2 times exponential minus 3t amp. Okay, next we look for a homogeneous solution. 好，我觉得解二阶微分方程式最主要有2个点哈，一个点是你一定要把第一个式子这个二阶微分方程式写出来。那你这边的式子怎么写呢？因为当然这有很多不同的写法，有时候会关系到你容不容易写出后面这个式子，所以你需要稍微练习一下，因为考试是有时间限制的，所以你这个式子有时候写的比较 不容易代换的话，你就比较会花一点时间写出这个式，所以你需要练习一下。然后下一步就是要解这个式子。所以如果 particular solution 跟 homogeneous， 尤其是我们刚刚讲 under damp， 它的那个运算上有时候比较复杂一点，因为有复数在里面。好，那像这一题我们是 over damp 会稍微容易一点，所以一定要请你稍微练习一下怎么样解这个，考试的时候比较写得出来。好。Homogeneous solution assumes in the same form a exponential as t and then put it in the previous equation here。 好，先把它代入，但是这一项左边这一项代为0，对不对？所以1/2 dIL dt 平方加3/2 IL dIL dt 加 IL。 好，所以把它带进去。好，那这边我们就直接写 characteristic equation。Okay, so we have s equal to -2 and -1. These are real numbers, so this is a case of overdamped. Okay, so we assume that 好，所以知道两个解，那我们 homogeneous solution 就有两项 a1 exponential -2t plus a2 exponential -t。Okay, so finally we only have two unknowns here, a1 and a2. Using two initial conditions. 哦，对不起，我们要先写 total solution. Particular solution plus homogeneous solution. Okay, when t equal to 0, the current is equal to 0. Okay, the voltage is equal to dIL dt plus 3IL. This is from our previous equations here. 好 ，VC 是 dIL dt plus 3IL. 好 ，so this is equal to A1 plus 2A2, which is equal to 10, the initial condition. Okay, so by using these two initial conditions, we have A1 equal to -14, A2 equal to 12. Okay, so that will give us a total solution 2 times exponential -3t -14 exponential -2t plus 12 exponential -t amp. Okay, when t greater than 0. Okay, so these are the two examples related to the second order differential equation, and then we are going to continue on lecture 11 that discuss about impedance. Okay, so last time we discussed that when we have a sinusoidal source, it's easier to convert it to its complex representation, VI, which is complex amplitude times exponential j omega t. And then in this case, for example, if we have R in series with C and then in series with a voltage source VI, the complex amplitude of VI is divided between the resistor R and a capacitor C that lead to a division, voltage division, which is equal to VP. This ratio is equal to 1 over SC divided by 1 over SC plus R. So if we take a look at the circuit, it looks like the resistor R is dividing the voltage with a capacitor which has an impedance of 1 over SC. Okay, so we define that the impedance is the ratio of the complex voltage across this component divided by the complex current of this component. So for a resistor, okay, the actual case is that we apply the sinusoidal current, over a resistor, so that I equal to I0 times cosine omega t. And then VR is equal to IR times R. If we convert it to exponential representation, so I tilde is equal to I0 times exponential st. Then VR tilde is equal to VR times exponential st, which is equal to IR tilde times R. Okay, so the ratio of this complex voltage divided by complex current is equal to R. So we said that the impedance of a resistor is equal to R.好，这边这个 impedance 呢，它是用来帮忙我们解决我们前面在讲的这个 sinusoidal steady state 的问题。好，那我们前面知道说，我们在解 sinusoidal steady state 的时候，其实比较容易把它转成 exponential 的表示法做运算，算完之后再取实部，就会是我们真正在电路上看到的这个 response。那转成这个复数 exponential 的表示法，它这个元件上面的 V 跟 I 的这个比例会有一个固定的值，那在电阻上面呢，这个值就是 R。所以如果今天真的可以给电阻一个电流源，这个电流源是 exponential st 的形式，那我们去观察这个电阻的跨压，它也会是所以如果今天这个电流源是上面这个 I0除以 exponential st 的形式，所以它其实是一个复数。那我们去观察电阻上面的跨压，这个跨压也是长得是这样子。好，那这个值会等于 IR 的这个 tilde 乘以 R。好，所以这个电阻上面，如果你去观察它的电压除以电流，比值会是 R。那这个比值呢，就跟如果你去观察，假设今天 I 是 sine wave 或者是其他的电流源的形式，它的 V 跟 I 的关系都会是 R。好，所以对于电阻来说，不管你今天给它的电流源是哪一种形式，是实数还是虚数还是负数，好，是一个定值，一个稳定的电流源 DC 或者是一个 sine wave， 在你去观察它的跨压，它的电压跟电流的比值都是一样，是 R。好，那用 complex 的形式推导出来 V 跟 I 的比值，这个值我们称为它是 impedance， 这个元件的 impedance。好，中文叫做阻抗。好，那我们上次讲到这边。好。Okay, next we consider the capacitor. Okay, so we know that for a capacitor, it follows the relationship that IC equal to C times dVC dt. Okay, so now similar cases, if we apply a voltage, a complex voltage across the capacitor, which is equal to capital VC times exponential ST。好，所以现在类似的状况，这个 complex amplitude 这个 VC 有什么？它有它的振幅跟它的相位。好，所以如果它转为实部的话呢，它会是有一个振幅 cosine omega t 加上它的相位，这样子，好不好？好，所以一样的，我们知道电容呢，它的 I 跟 C 的关系符合 I 等于 C 底 V 底 T 这个式子。那如果今天我们真的可以放一个负数的这个电压源在这个电容的两端，好，那这个负数的电压源它是这个形式，大写的 VC 乘以 exponential ST， 这个 S 是 J omega 哈，所以它是一个负数。然后我们去观察流过电容的这个电流，好，那不管今天我们在这个两端的跨压是什么，它的电流跟电压会符合这个式子，好，所以我们就把这个 VC 跟 IC 带入这个式子，好，那会把这个大写的 VC 跟大写的 IC 它们的比值可以算得出来，这个比值是1除以 SC。Okay, so this ratio means that if we apply a complex voltage across a capacitor, and then we take a look at the current going over the capacitor, the complex amplitude divided by the complex amplitude of the voltage divided by the complex amplitude of the current going through the capacitor is equal to this value. So we said that the impedance of a capacitor is equal to 1 over SC. Okay, so this is what we write here. The complex amplitude, which means VC divided by IC, are related as 1 over SC. Okay, we also know that S is equal to J omega. So we know that we conclude that the impedance of a capacitor is inverse proportional to the frequency. Okay, so we said that when frequency approaches 0, this impedance approaches infinity, which is the case that we said in the previous lecture when we have a DC operation, when omega approaches 0, a capacitor acts as an open circuit. Okay, when we operate at high frequency, this impedance approaches 0, so that the capacitor acts as a short circuit. Okay, the impedance we usually use capital Z to represent it. So impedance of capacitor can be written as ZC. 好，那这边我们再说一次 impedance。好，我刚刚口头讲的 ，if we have a component and then we apply a voltage across it, this voltage is a sine wave. And then we observe the current of this component. 好，那一般来说，if the component is a linear component, we know that the resulting current is in the same frequency as the voltage, but it will have a different amplitude and a different phase. 好，所以如果给它 Vt， 这个 Vt 是上面的这个式子，好，它有它的特定的振幅、它的频率跟它的相位。然后你去观察流经它的电流，它有它特定的振幅跟相位，但是它会是在一样的频率。好，那我们当然想知道 V 跟 I 是什么样的关系。But it will be difficult to analyze a circuit if they are sinusoidal. So we convert it into its complex representation that V is equal to Vm.这边应该加绝对值比较好哈。后面这个，我想一下，好，不用，OK。好，所以实际上这个 complex amplitude 是这样 ，J omega T 再乘以这个。好，那取10步就会回到左边。好，所以它有一个振幅，一个相位。好，那它的频率是 omega。Okay, impedance is defined by this capital V divided by this capital I. 好。那阻抗的定义是我们假想的这个负数的电压放在我们的元件上，观察这个负数的电流，这个电压跟电流的比值定义为 impedance。好，所以你知道它其实可能是一个负数，它有它的振幅跟相位。好，那 impedance is usually written as capital Z, which is a complex number. The real part is usually denoted by R. The imaginary part is usually denoted by X. Okay, so R, 这个 R 就是我们常见的，so R is called the resistance. And then X is called the reactance. Okay, this is also in the unit of ohms. 好，所以 R 跟 X 的单位都一样，是欧姆。好， when X is greater than 0, then it is an inductive impedance. Okay, if X is smaller than 0, then it is a capacitive component. 好，所以像我们刚刚的电容 ，for the capacitor we mentioned that the impedance is equal to 1 over j omega c, which is minus j times 1 over omega c, which is a negative imaginary part. So it means that this component is capacitive. Okay, so back to our analysis if we have an inductor. 好，所以我们刚才没有讲这个电感的状况。Okay, for an inductor, we know that the voltage is equal to L times di dt. Okay, so it doesn't matter what is the form of current and voltage across a capacitor inductor. You always follow that V is equal to L di dt. Okay, again, now if we apply a sinusoidal voltage across the inductor. How? In analysis, we need to convert it into its phasor representation. So the complex voltage across the inductor is equal to capital VL times exponential ST. The current is equal to IL times exponential ST. And then we put it back in this equation. So VL exponential ST is equal to L times the differentiation of IL. So that we have VL divided by IL is equal to S times L. Okay, which is the impedance of an inductor, and then you can also write it as J omega L. So that the impedance of an inductor is proportional to its frequency. When frequency approaches 0, this impedance approaches 0, which is a short circuit. Okay, when frequency approaches infinity, this value approaches infinity, which is an open circuit. « 好，我们休息5分钟好了，好吧？ 好，我们再来上课。这个讲到 impedance 是因为我们刚刚讲，就是顺着上一章 sinusoidal steady state 直接写三角函数，计算上比较复杂，所以我们用它的 exponential 的这个表示法来解。那就有人发现说，其实它有一些规则。我们上一章直接解 exponential 的用 exponential 这个复数的讯号源来解，它还是有一些计算的过程。那就有人发现说，他们其实有些规则，然后这样子算会更容易。好，所以就是引入这个 impedance 的概念。好，所以 impedance 的概念基本上就是我们在它两端给一个复数的这个 exponential 的电压，那去观察它的电压跟电流的比值。好，那这个电压呢，它有它的正负跟相位，电流有它的正负跟相位，所以是电压的正负跟相位除以电流的正负跟相位，这样子。好。Okay, so a summary, if we have a resistor, the impedance is equal to R, which is the resistance of a resistor, so that the phase is equal to 0 degrees and its magnitude is equal to R. If we have a capacitor, its impedance is equal to 1 over j omega c, so that the phase is equal to, 这个 phase 是什么？在这个复数的平面上面 ，where is 1 over j omega c？ 这个我们刚刚有说负 j 乘以1除以 omega c，right？ So it's in the negative y-axis。好，所以是在负 j 是在这个地方，所以是负90度 ，OK？ So the angle, the phase of a capacitor is equal to minus 90 degrees, and its magnitude is equal to 1 over omega c. For the inductor, its impedance is equal to j omega L. Okay, so the phase is equal to 90 degrees. 是在 y 轴，它只有虚部j omega L 会是在正的这个 y 轴90度， and then the magnitude is equal to omega L. Okay, so to conclude, for a drive in the form of Vc times exponential j omega t. 好，那这个 Vc 就一样，它有它的正负跟它的这个相位。The complex amplitude Vc is related to the complex amplitude Ic algebraically by a generalization of Ohm's law. So Vc divided by Ic would be equal to the impedance of the component. Okay, so back to our RC circuit. Okay, so this is the circuit that we analyze. And then the question is to find Vc. 好，这是我们之前的电路嘛，然后我们之前就说，这个是一个 sine wave， 然后呢，想要知道这个 Vc 挂在电容上面的电压是多少。好，那现在呢 ，what we do here using impedance, the concept of impedance is that firstly we convert the source into the complex amplitude Vi. And then we build the impedance circuit model. So the impedance of a resistor is equal to R. The impedance of a capacitor is equal to 1 over SC. Okay, so now the voltage across 1 over SC is denoted by capital VC, which is the complex amplitude of the voltage across capacitor. Okay, so by using KCL, we have the the current of a resistor is equal to the current of a capacitor. So we can write VC is equal to VI times 1 over SC divided by 1 over SC plus R. Okay, which is the same as what we did in the previous lecture. 好，你想象一下，上一章呢，我们是假设这个，然后呢，我们先把它转成它的这个 exponential 的表示法。好，然后呢，我们就把这个一阶微分方程式列出来 ，RC 的一阶微分方程式列出来，然后这个是我们的 source， 把它带进去解，对不对？解完之后就会得到一个 complex。看一下，好。In the previous lecture, we list the first order differential equation, which is equal to this. And then instead of this source, we use its exponential representation. 所以把这个本来是写 vi cosine omega t 的地方带成它的这个复数的表示法 vi exponential st。带进去之后呢，假设 particular solution 是某一个形式，带进去算，然后 homogeneous solution 是一样的。好，那算出来之后呢，我们取10步，就会得到我们最后的这个解，这样子。好，那我们的这个复数运算到最后，最重要的是 complex amplitude 这一项。好，那这一项呢，就是我们刚刚写的那一项是一模一样的 ，vi 除以1加上 j omega rc。好 ，which is equal to this term vi times。如果你把它稍微化简一下，上下multiply sc in both numerator and denominator scr。And then S is equal to j omega. 好 so this is the same complex amplitude as we calculated in the previous lecture. 好，所以上一章我们就是解到这边，然后取10步就得到我们的答案。那这一章呢，我们就会发现，你用 impedance model it's much easier if you use impedance model. So convert the original circuit into its complex representation. This is a complex amplitude of the voltage source. This is a complex voltage across the capacitor. This is a complex current going through the capacitor. Capacitor use its impedance in this circuit, 1 over SC. Resistor keep the same impedance, which is equal to R. So it's easy to write by using KCL that you have VC equal to this value, which is the complex amplitude that we solve in the previous lecture. So so what you do now is you only need to take the real part of this. 这就跟上一章做的一样，对不对？ So you take the real part that will be equal to VC, which is a sinusoidal response of this circuit. Okay, and if you take a look, the denominator is equal to the characteristic equation. Okay, next we will summarize the notation of different type of signal here. Okay, so in each representation we have a regular letter and its subscript. Okay, if the letter itself is capital, so uppercase, and then the subscript is also uppercase, then it means usually it means a DC variable. 好，这一页我们在讲，我们前面常在写 V 跟 I， 有时候大写，有时候小写。好，那它的下标有时候会大写或小写。这边在讲的是通常大家通用的一些什么时候写大写，什么时候写小写。那并不是100%，不过未来如果你学，比如说你去学讯号系统啊，学尤其是在电子学、电路学或电子电路或是延伸的课程，大致上80%都是这样子。好。所以，如果你的字母本身是大写的 V 或大写的 I， 你的下标本身也是大写，它是so you can think of that as a constant voltage or a constant current source. So it does not change over time. Okay, operating point meaning that the voltage the constant voltage you provided to operate the device. This is usually for an active device. 好，这个 operating point 我们现在没有教到，这个是操作的点。那一般来说，你在操作主动元件的时候，你需要给它特定的电压值，它会操作在某一个特定的模式，你就可以使用。好。If we have a lowercase symbol and an uppercase subscript. Oh, okay, so for example, this can be equal to, for example, 10 volt or the current equal to 1 amp. Okay, so it's a constant. The second case, it means the total instantaneous variable, so that could include a DC plus an AC term. Okay, so usually it's a DC plus an AC term. Okay, so for example, that would be 10 plus a cosine. 好，所以这个第二种状况呢，是指如果你去观察一个元件，它的电压，瞬时的电压。好，那瞬时的电压呢，它有可能本来它就有一个操作点，就像我们刚刚讲的，你本来就有给它一个电压源，那这个时候它又有讯号经过它，讯号经过它会改变它的这个 VI 的值。好。所以基本上它就是有直流跟交流的讯号在上面，是一个总和。好，这是我们的第二种状况。If we have lower letter, lower symbols, and then lower subscript. Okay, it's the incremental instantaneous variable. So usually it's only an AC signal. Incremental meaning that on top of the DC, what is this varying part? Okay, so usually it's an AC part. 这个 incremental 通常就是指你在某一个特定操作点，因为你有讯号的关系，它会上下的变动。那这个上下变动的量有多少？好，所以通常第二个 for the second one, you can think of that as the first one plus the third one. Okay, the last one, if we have capital symbol and then lower subscript, that's the most common one for complex representation for a complex amplitude. Okay, just for your reference, so this is out of the scope of our text. 大家可能不知道上面那个有点没有概念，那我画一个图，但这个当然不会考，给大家参考。好，what I draw here, you can think of that as an amplifier. Okay, in the amplifier we have one transistor. 好，所以我画的这个你可以想象它就是一个放大器这样子。好，那一个放大器里面其实就是电晶体，这个电晶体就是你在数位电路学到的开关，也是用电晶体做的，所以 this is a transistor, an active device. Okay, this active device has 3 terminals. So for example, a resistor has 2 terminals. Okay, terminal 1, terminal 2. So this is a device that has 3 terminals. 好，所以这3只脚呢 you have to provide each of them a fixed voltage to operate it as an amplifier. 好，所以如果你要把它当成放大器，假设在我的这个例子里面，那这3个点呢 you need to provide it a constant voltage. 好，所以这个 constant voltage, which is this, the operating point. 好，所以呢，通常 usually this is connected to ground, which is 0 volt. Okay, the upper one is usually connected to, for example, 2 volt by a resistor. So this 2 volt set a voltage at this terminal. 好，然后呢，接下来最后这个点呢，好，那这个2 volt is actually also connected to a voltage source. 好，所以这个2 volt 你可以想象成第一个。我们刚刚写的第一个 capital V and then capital I. For example, 1 volt. 好 So if you connected 2 volt to the top, 1 volt at the left, and 0 volt at the bottom, it is the case where this transistor can be an amplifier. But now you don't have any signal to be amplified. So这个呢，是我们先给它特定的直流的电压值，这个时候你的电晶体可以当成一个放大器，但这时候它并没有在放大，因为放大是要放大一个讯号，我们并没有把讯号加进来，所以这个1伏、0伏、2伏就是我们前面讲的这个 DC 或者是它的操作点，你让它操作在某一个状况下，它可以当成它可以有你要的这个功能。好，那这个时候呢，好，那我画的很简略，那实际上可能会复杂一点，比如说中间会有电阻等等，那这个我们就不说。好，那这个时候呢 ，if you want to operate it as an amplifier, we need to feed the signal into the circuit. 所以如果我要当成放大器，我当然是需要把我要放大的这个讯号放进去。好，所以如果今天我要放大一个 sine wave, so I also need to connect a sine wave into the circuit. There are different ways you can do that. 那我们比较简单的做法，好，这个1伏我们还是留着，但是呢，我就把这个 sine wave 把它加进来。Okay, so now for example, I'm going to amplify 0.1 cosine omega t. 好，所以我把我的讯号就加到这个1伏的电压源里面。那这个就是我们刚刚讲的第二种状况，这里面有一个直流跟一个交流的讯号。好，那这个直流是为了让我的这一只脚它的直流电压值是1伏，这个交流的讯号是我们想要放大的讯号，这样子。好，那这个交流的讯号呢，它会放大，所以如果你观察这一个节点的这个电压值，它就会变成它，比如说放大10倍，那就会变成1乘以 cosine omega t. So if you take a look at the voltage here, you will see 2 volt, which is the operating point at this terminal, plus 1 times cosine omega t. Okay, so this part is the incremental. 这是我们刚刚讲的第3种。这个 incremental 是因为我们把这个讯号放大。好，那实际上在这个点上面，它其实如果你去看它的话 ，over time 它会怎么样？它会中心在2伏，然后呢，它会这样子上下震荡。好，所以2加上 cosine omega t 是我们的刚刚讲的第2项，有 DC 也有这个交流。好，那如果只考虑这个交流的部分，那就是我们讲的第3项这样子。哦，好，所以只是让大家知道一下。那未来你在学电子学或者是其他的类比电路、集体电路课程，这个到底哪一个是我们讲的第1项 DC 跟它的 operating point， 哪一个部分是真正的讯号要拿来做一些事情？好，可能是放大，可能是其他的事情，它们2个要有所区别。那这件事还蛮重要的。好，那这是题外话，让大家知道一下。好 ，so now in this lecture we apply impedance model. So basically, first we replace the sinusoidal source by their complex amplitude. So again, a complex a sinusoidal with a certain amplitude and phase is converted to its complex representation, and the complex amplitude is equal to VI times AJ theta. 好，所以我们假设这个是我们讯号源的 complex amplitude. And then we place each circuit element by their impedance. So if you have an inductor in the circuit, you need to write it as SL. If you have a capacitor, you need to write it as 1 over SC. If you have a resistor, then you just keep it as R. So this circuit diagram is called the impedance model of the circuit. Okay, so which is the right one. 好，所以如果本来电路 if the question is on the left, and then I ask you to draw the impedance model of the circuit, you need to convert it to the right. Okay, so again, convert each voltage or current into its complex amplitude. Convert each component into its impedance. Okay, so by going from the left to the right, we find the impedance model of the original circuit. 好，所以如果问题，请你画这个电路，我们题目是给左边的，请你画出它的 impedance model， 你要把右边换出来。电压跟电流呢，本来从这个它是 sine wave 的形式，换成它的 complex amplitude 的写法。好，那每一个元件换成它的这个阻抗值。Okay, and then from that, determine the complex amplitude of the voltage and current in the circuit using any standard circuit analysis method. So you can now apply all the analysis method we learned in lecture 2 and lecture 3. 所以前面所学的所有superposition, node analysis, mesh analysis, Norton, Thevenin's， 只要我们的电路是线性的，前面学的你全部都可以用。那你用的时候呢，你就需要用 complex amplitude 来做计算。好 ，and then find， 然后最后呢，我们会得到一个 complex amplitude， 找它的实部。Find the real part of the complex amplitude, and then that's the for example, for the complex amplitude. 好，所以如果你的 response 它的这个 complex amplitude 是 V0， 那你就把 V0 的实部找出来，就会是 that would be the sinusoidal steady state response. Okay, so which is the amplitude of the complex magnitude, and then the phase of the complex amplitude. Okay, once you are familiar with this, you will find it very much more easier to solve the sinusoidal steady state.我们接下来想考in Wednesday's quiz, we won't cover this, so this part will only be covered in the final exam. That in the question, I will specify to use the impedance model to solve the sinusoidal steady state, or to use what we learned in the previous lecture to solve for the sinusoidal steady state. So that will be clearly specified in the questions. Okay. 所以这一章跟上一章我们其实在解一样的问题。上一章呢，我们是用 complex amplitude 取它的实部，得到最后的 sinusoidal steady state response。这一章呢，我们是把它转成复数之后，用 impedance 的方式来解这个 complex amplitude， 最后也是要找实部，转成最后的这个 sinusoidal steady state response。所以两种方法都可以做，当然这个做法会比上一章的更容易。在期末考的时候呢，我在题目里面就会写，请你用 impedance 的方法做，或者是请你用上一章，把电流源或电压源换成复数的表示法，去解这个复数的，去解这个一阶微分方程、一阶电路的复数的表示法的式子，得到 complex amplitude。好，所以我在题目里面会写。好 ，one more example. Now, if we have series RLC circuit.好，你就放在前面就好。这是哪两章？11跟10。好，如果你需要11章的讲义，可以现在先到前面拿。好，然后我们有12章的讲义，下课如果你需要，可以过来拿。Okay, so in this question we have series RLC, and then assume the source is equal to VI times cosine omega t. Find the voltage across the resistor. If we are going to use the impedance model, so first I'm going to convert it into capital VI, which is the complex amplitude of the voltage source. Okay, in this case, which is equal to VI times exponential j omega t. And then I'm going to convert L to j omega L and then convert C to 1 over J omega C. Okay, so now I'm going to apply KVL. So basically, this is also a voltage divider between 3 components. So the voltage, okay, and also I'm going to convert it into the complex amplitude of VR. 好，我们刚刚讲一般这个小写比较多。好。Okay, so VR is now equal to R divided by R plus J omega L plus 1 over J omega C times VI. Okay, so the first step, we convert it to impedance model. Okay, the next one, we can write the complex amplitude of VR in terms of VI. 好. The next, we just take the real part of capital VR.好，那我们把这个第二步大写的这个 VR 取它的实部，就会是我们最后的答案。Okay, so this will be the final solution. The sinusoidal response of the voltage over a resistor due to a sinusoidal voltage source equal to this. 好，所以真实的情况是我们把一个 sine wave 施加到这个 RLC 的电路，然后我们想知道这个 sine wave 施加到 RLC 电路的时候，我的电阻的跨压会是多少？那电阻的跨压也会是一个 sine wave， 可是跟我原本的 sine wave 会有不同的振幅跟相位，所以我们重点是要找出它的振幅跟相位。好。那我们先把它换成 impedance model， 换成 impedance model 的时候，我们假设这个电压源呢，它现在变成一个复数的形式 ，VI 大写的 VI 乘以 exponential J omega t。那这个电路实际上是 VI 在3个元件里面做分压，所以用 KVL 就可以把 VR 这个是 complex amplitude 的这个 VR 把它写出来。Okay, so this is a voltage divider. Okay, so the actual response of the voltage across the resistor is equal to the real part of this. This is a complex number. 好，所以到时候，比如说这个 VI 会是一个定值，你把它带进去，这个 RLC 的值带进去，这是一个复数，你要解出它的振幅跟相位，好，把它带进来。那这个是实际上我们施加这个 cosine 给电路的时候，你真正在电阻上面观察到的电压就是这样子。好 ，and then remember we plot the magnitude and the phase of the transfer function of the circuit. In the previous lecture, we defined the transfer function equal to VR divided by VI. Okay, usually it's the response divided by the excitation, which is R divided by R plus J omega L plus 1 over J omega C. This graph is optional, so it's a little complicated to draw this. 因为我们现在这个式子就变比较复杂，没有那么容易，对不对？好，那我画给大家看这张图。如果我们有空在以后我们会再说，如果没有的话，我们考试不会考你画这张图。好，you can think about it if we plot it over frequency. So if we are at very low frequency, what happens? 频率很低的时候，这张图是 V 跟 VR 跟 VI 的比值。好，所以给定某一个特定的 VI， 想要知道这个 VR 到底是大还是小。好，频率很低的时候 ，when we are at very low frequency, this term is approaching zero, right? When omega is approaching zero. So L is a short circuit, but now C is an open circuit, right? When omega approaches zero. So if this is an open circuit, it's not a closed loop here, so we don't have a current. So that this voltage across the resistor is equal to zero. Okay, so this term is equal to zero. So at low frequency, due to the open of the capacitor, VR is very small. Okay. Okay, and then you can think about it when we have when frequency increases, 1 over J omega C 会怎样 ？omega 慢慢增加的时候，电容的这个1 over J omega C decreases, but J omega L increases. Okay, so it's a combination of L, the impedance of L and C. Okay, so in reality, when frequency increases, it will start to increase. So you will see the increase in the voltage across the capacitor to a point where it depends on the value of L and C, to a point where it reaches 因为这是一个二阶的方程式，如果你画它的正负，所以你可以想象它一定是一个二阶方程式的曲线。好，那跟 LC 的值有关，它一定会达到一个最高点 ，and then you start to decrease. Okay, so when frequency is very high, now inductor look like an open circuit. So again, VR decreases to zero. 好，所以它画起来是这样子。好，那 this is it has a bandpass characteristic that only a certain band can pass through the circuit to be the voltage across the resistor. Otherwise, when you have very low frequency or very high frequency cosine, you don't see that across VR. 好，我们就上到这边。
但你会发现最后你真的如果在实作的时候 ，OK， 很多如果你 data 够多的话，实作上你会发现很多其实就是 transformer base 的事情 ，OK， 因为它是一个有一点是把 LCN 这些都换掉了 ，OK， 把很多时候其实把 convolution neural network 也有点换掉了 ，OK， 它其实就是个 transformer 为基底的一个方法，因为它其实你可以想想很多的，这刚刚我们讲的方法学都是 transformer 的一个 special case 嘛。OK， 其实这个 special case， 如果 我的 convolution 在这个区间有个值 ，OK， 大小小，因为它也是点乘嘛，然后 activation 乘起来嘛，所以我如果这两个位置它 local 区间很近 ，OK， 位置附近很近，然后我乘上一个 W 乘上一个 QK 这个，然后再开一个 attention 值大，它其实是一样的意思 ，OK， 就是说它其实就是那个其实就是 transformer 的一个比较小版的东西而已 ，OK， 那但它还没办法扩散到其他的区间，所以 transformer 它很多时候会代替了这些做法，然后因为它的做法又是刚刚那个 attention 的计算的方法，所以都很快 ，OK， 所以然后又没有 recurrent，recurrent 就是很麻烦，它没办法同时一起做嘛。我现在如果一个 sequence， 我现在可以同时一起做，可以说 sequence 一进来，我全部算 attention， 全部就是走。那 recurrent 我就是一定要等它转，我这个乘完再乘下一轮，再乘下一轮，再乘下一轮，乘到我乘到那个位置，我才知道我乘了多少进来。OK， 那我 attention 不用，我会同时就直接下去这样子。OK， 好，所以这是一些比较近期的方法跟大家分享了。不过大家不用担心考试这个很难考，所以大家也不会考这一块。但是大家就是有个概念说，OK， 现在 transformer 是长这样，那到时候大家上 DIY 课程的时候，他可能老师那 NVIDIA 老师应该也会再稍微带到一点这个观念那样子。OK， 好，那我们上课就到这边。